Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello and a warm welcome to the Trustworthy AI webinar series. My name is Wojciech Zamek. I'm professor at TU Berlin and head of the AI department at Fraunhofer HHI in Berlin. And it's a great pleasure to present today's speaker, José Hernández-Orallo. José is professor at the University Politécnica de Valencia in Spain and a senior research fellow at the Leverhulme Center for the Future of Intelligence at the University of Cambridge in UK. He is computer scientist by background and did his PhD in logic and philosophy of science with the École Nationale Supérieure de l'Électronique et des Applications in France. His research focuses mainly on several areas of machine learning, artificial intelligence, intelligent measurements, with a special focus on more insightful analysis of the capabilities, the generality, progress, impact, and risks of artificial intelligence. So I very much look forward to your talk today, José, and with that, the floor is yours.
Thank you, Wojciech, for the introduction and for having me here today. It's a pleasure to be in this series, talking about ideas around AI for good and more specifically about Trustworthy AI. And I'm going to share my screen in a moment so that you can see my slides. So I've been intentionally provocative with the title, so don't trust your AI system, but that will be more constructive as we move on during the presentation, proposing in a way that there's an alternative or a complementary approach of some other existing ideas or approaches to make AI more trustworthy, which is modeling the validity or the invalidity when systems fail of AI systems in particular. So I'll start with a kind of a vision to see that this problem or some problems are going to be aggravated rather than eliminated in the future. And this is based on something that we are realizing already. So humans, we think we are smart, and because we are smart, we have or we will create smarter AI systems. So in this scene, one can think that perhaps the solution to control these smart AI systems is, well, maybe there's no need to control them because we trust them, because we have designed them. So yeah, we can imagine that we have done that well. But the vision for the future is that for many applications, and even in midterm in some more general domains, it can be even smarter than us. Then this idea of trust is limited, is challenged by being trained to be able to understand, or if you don't understand the system at least is aligned with us. So these two questions of understanding and alignment have been around for some quite time, about, especially this vision of a smart and a smarter systems that can go out of control. But even at more domain-specific applications where we can have things in control, there are many cases where these systems find more sophisticated patterns that we can find, and they can do things in a smarter way than we can do. And that's exactly why we want these systems. It's not that we want just how to automate what we do, is that we want them to do some other things or do things better than we do. But what if, as these systems become more complex, smarter, then this understanding and this alignment becomes more and more difficult. Of course, there's a kind of a tension here about the complexity, the increasing complexity of these systems, their capabilities, and also the tools that we introduce to understand them. This tension is going to be there, but there will be moments where this tension will be taking one direction or another. So maybe there were situations or kinds of systems where this understanding or this alignment is not impossible. So, of course, the one of the outcomes is that we say, okay, because we don't understand the system, or we cannot perfectly align the system shouldn't be used, shouldn't be deployed. That's, of course, an option, but maybe in some situations, there's something else that we can do. So there's a kind of understanding, and I'm not saying that everybody agrees with this view, but many people will find some kind of truth under this statement that trustworthy AI relies mostly on performance and understanding. Maybe understanding, we could just put that under the label of explainable AI. So if my system is highly reliable, so imagine that we have a self-driving car and it works well 99.99% of the times, that's perhaps even better than humans on average. And we can explain the 0.01% that remains, then I think we have a kind of a nice picture. So a very reliable system, and when it fails, we know why. Why shouldn't we trust the system? Well, I'm going to argue that there are two main reasons why we shouldn't. The first one is performance, and the second one is understanding or explanation. So, and I'm saying that performance is necessary. If a system is not really performing well, of course, it's not going to be very useful. And of course, if we don't understand the system, there are many dangers associated with the use of these systems. So these things are necessary, but maybe not enough. And we will see why. So the first thing that we have to clarify is that performance is not the same as capability. And this is very important. And this is the source of many discussions about limitations and problems and surprises of AI systems. So what's performance and what's capability? So in psychology, this is more clear than in computer science, for instance. But performance is a property or measure or measurement of a per system item. So we can say that my spam filter that I use with my email application has a correct prediction on this email message. That's performance. So that's this system with this item that in this case is correct. We can aggregate population alone. We can say that, for instance, this neural network is 85% accurate with the instances in ImageNet, or some kind of a test set or deployment set, or some kind of a subset of the original data set, ImageNet. But of course, because this is a property of a system item, whenever the distribution changes, my performance is going to change. So on blurry, adversarial, out of distribution images, in the case of ImageNet, the result is going to be much worse. And that's why, and of course, this is expectable, people sometimes get surprised that the system behaves so badly when we change the distribution, because basically that's, if we are changing this distribution, performance is going to change. This is natural, and this also happens with humans. Of course, in different ways, and that's why we have sometimes we have surprises. We expect these kind of deviations to happen perhaps differently. But capability is a property of a system, not of a pair system item. So a system can add integers up to 3 digits, or a system can jump up to 1.20 meters high. These are properties of the system. So if I put a lot of examples or easy examples or a lot of difficult examples in my distribution, still the capability is the same. The system can add integers up to 3 digits, and the system can jump up to 1.20 meters high. Of course, all the other things being the same, or all the elements that affect performance have been identified. In this case, just the size of the number of digits in addition, or the height of a bar in high jump, for instance. If there are some other elements, we need to also understand how these elements affect performance, and then we will have more than one capabilities or a multidimensional capability or capability profile. But the interesting thing is this distinction. So many of the discussions about having good performance on what? It's because if that what is going to change, then I don't trust the system. Or I don't know whether the distribution is going to change, or the distribution is not a good sample of the working distribution. So all of these problems come from this evaluation of performance. If you just, especially when we aggregate numbers and say 99% performance, so we have no patterns of performance, we don't know where it fails and why, or what features. And this, of course, will take us to explainable AI in a moment, that tries to do a little bit of this. And there's poor estimation of performance from your distribution that I was referring to. Many times this metric cannot be extrapolated when we change the distribution just a little bit. And even inside the same distribution, even if we don't change the distribution, we cannot really anticipate how the system is going to behave for each particular instance. And that's something, as I will argue in a moment, that we can do. And it is not usually done in AI. And it's been done in other areas, so it's not something that we have invented. It's something that perhaps we have to bring from some other areas, starting from software engineering and some other areas outside computer science. So this takes us in, especially some of the first questions, in the direction of understanding why systems, how systems behave. Well, I claim that explainable AI is necessary. Necessary is a very important word, so but not enough. Maybe that we need some other complementary things. Just understanding a system and having high performance is not enough. So one of the things that we can do, this is perhaps not the usual approach in explainable AI, but many explainable AI systems, they try to ask the question of where things fail or where systems fail. So one way of doing this is just to identify conditions. So for instance, in this case, we have a self-driving car and we have two conditions that we think that affect performance. One is fogginess, and another we call it windingness, or how convoluted the road is. So you see on the right, we can have many systems that have 62.5% aggregate score, but this score can be distributed in many different ways according to these two dimensions. For instance, on the top left, we have that only windiness is predictive of performance. It gets really red at the top. But fogginess is not relevant, maybe because the car has some kind of a special vision system where fog is not really relevant for performance. That might be the case. You can have the other way around, or you can have, as usual, that these two things affect at the same time in different ways. And that's what you see in the second column, where you see this kind of green going from the bottom left to the top right of some of these plots you see with red and green and yellow colors. But there might be a situation where you see something on the right. When you see on the right, it's kind of a mess. You don't see any pattern, or these two dimensions, they don't explain at all why you get 62%, 62.5% for this problem. So there are many situations, and that's one of the approaches, identifying the dimensions for success and failure. And this is one possible way of approaching the question of where things are, where in terms of examples, in terms of features. And some of these features might be different from the original features of the problem. They might be just features to predict. And that's what we will discuss in a moment, just to anticipate failure. Of course, some other questions that have been covered in explainable AI is, why did it fail? And here, especially, we have a complex situation such as a self-driving car. We can just say, or even at a legal level, what's the ultimate reason of an accident? It was the AI system, it was just the conditions, it was this and that, it was a human, if there was some kind of a semi-assisted use of technology. Well, this is complicated, and typically when you're looking for a cause, just leave it to the police and just to the investigation to analyze what is the cause. It is very difficult to understand, especially if we have hybrid systems. What's the ultimate cause? Or maybe there are several causes, and every accident usually requires a complex investigation of this. So that goes much beyond, in many cases, some of the tools that we have in explainable AI. That means that I'm not saying that this is impossible, but we will have to just, there's still a lot of challenges ahead, especially we want to ask causal questions about why. And because there's some other questions about what, because they haven't been so analyzed until very recently. And I think that's a good direction. But yeah, asking some of these questions, where, why, and what, perhaps, as well. So there's some problems of, I think that explainable AI is very powerful when you want to explain how a system works for experts, AI developers, domain experts. Okay, I know how cars, the system, have been involved in the development of the system. I know about conditions in driving, and then I use this explainable AI system, and I see where it fails, and I can understand. I can just make some revisions on the system. This is very promising, and it's already working very well in some applications. And this is making our systems much better than they would be without explainable AI. But there's also a dangerous use of explainable AI for what I would call mortal users, non-experts. So if you are a user of a car, but you haven't been involved in the development of the self-driving car, and you're just there as a passenger, well, the company using, maybe they can use this explainable AI to give you a justification, rather than to revise how their systems work. Because this has happened in many other areas. This is not new for AI, and then this idea of how complaints are dealt with in many companies. Basically, what you have is, instead of, you have excuses rather than explanations. But there's a danger that some organizations can start using some of these explainable AI tools for the purpose of getting some kind of overconfidence on the users, because there's a pressure. And then in the end, we have a kind of a dangerous calibration of trust. So that's why I use this provocative title about "Don't trust your AI system," or at least don't trust as much as, especially if you're a user, don't trust it as much as perhaps the company trying to sell you the system would like to. So yeah, so being a little bit even under-calibrated, or having underconfidence rather than overconfidence on this system, I think it's a safer stance on AI systems. And there's also this idea of false sense of understanding. Sometimes, okay, you didn't get this parcel from Amazon or any other because the truck had a problem, and then sorry, but we will deliver your parcel tomorrow. Is that an explanation? Is that an excuse? Is that true? I think if you get many of these emails and there's no predictability in them, you don't know, basically there's no anticipation, you are not going to trust the company anymore. So this leads us to the question, if prediction is so important for trust, and these systems are becoming more and more complex, is it impossible? It's going to become impossible to predict what they do. And I'll go over that in a moment, but we have been trying to build surrogates for very complex neural networks using maybe decision trees or something like that. And there's a trade-off there, but basically we realize that we cannot really mimic the whole behavior of the system in terms, in ways in which humans can understand the whole behavior of the system. So complete behavior is impossible in many cases. So, but still we trust what is predictable. And can we just change this post-analysis of why it failed into when and where it will fail? So this is a bit more anticipative or predictable. Can we just move in that direction a little? Now the explanation and prediction are closely related. So basically where we are trying to change the focus a little bit. It's not, we are saying that, of course, this is completely independent from what has been done in explainable AI. I'll argue that there's a lot of connection, but this is just a change of perspective, just instead of explaining what has happened, predicting what is going to happen. But as I said, predicting behavior is very, very difficult. We cannot predict system behavior in details. We cannot predict what human people are going to do at many levels. And even if we try to model that with some other more comprehensible, interpretable models, it has been tried, and you have to find this fidelity interpretability trade-off, and we lose a lot of information in that process, and we don't get proper understanding in many cases, especially as these systems are doing things in ways where their ontologies, features, and processes are very, very different from our processes. Many cases they use completely different perceptual systems. They use a radar and we use vision. So if a system uses vision, still there's a kind of many things that we can do, but in other cases, if the perceptual system or the perceptual system of a robot is completely different from us, it's very difficult for us to understand why the system is doing this or doing that. But even if we can't predict what the system will do, we can predict the outcome. We can predict whether it is going to be good or bad, it's going to be successful or not. That's, in many cases, that's an easier problem than the original problem. So predicting outcome or predicting failure that has been addressed in many other systems, software systems and mechanical systems, and we can do the same for AI. That may require less power than just trying to mimic the original model, and it is still useful if we don't understand. If we can predict and we don't understand, it's worse, and if we predict and we understand, it's still useful. So I think I would like to dissociate these two things. So, for instance, we can answer questions like, I don't know what the speed of the car is going to be. I don't know if the car is going to stop. I don't know which turn the car is going to go off. I don't know any of these details, and it is very difficult to predict. But I can predict that there's a high probability that something will go wrong. So in many cases, it's easier, depending on the conditions of the problem, to predict the outcome of the application of a system to that instance. What we can't predict is exactly what is going to happen, but that something wrong is going to happen, that's something highly predictable in this case. So what are the approaches for this predictable AI? So one approach is to predict from capabilities, and then a second approach that I and my team, we have investigated is predictable AI from assessors. So predicting AI from capabilities is something that is based on cognitive science or even psychology. So you extract some capabilities, and from those capabilities, you try to predict how the system is going to behave or what is the outcome of that system according to some of the features of the problem. These features are usually meta features that are predictable about success. So I'm going to go through one example that so 4 years ago, we organized the Animal AI Olympics, which was an reinforcement learning competition using problems inspired by animal cognition and comparative cognition with animals that we brought to a virtual arena. And then we had a competition with many participants using mostly reinforcement learning techniques, deep reinforcement learning techniques, and we had the results for the instances of the problems for all of these 68 participants. So we took this, that's something that we did this year. We took the results and we identified the features that were interesting, or they were just relevant, or maybe they should be irrelevant for success. So clearly the size of the ball, the reward, this green ball that you see, the size of the wall, the size of the reward, the distance of the reward, and whether it is in front or behind, that these features, or these meta features, you want to call them, are like that, they are really, really relevant. And some of that should be less relevant or irrelevant, maybe whether the reward is on the right or on the left, and the color, maybe green and yellow, if these have the same value in the system. So we check that on the population of agents, and all of these agents we got the results from, and yeah, the first three are the reward size, reward distance, and the Y position, whether it is in front of you or behind you, behind the agent, and then the X bars, which is an example of an irrelevant feature. So here what we see is the first three, of course, these features are ordered from easier, difficult to more difficult, and we see decreasing curves. Of course, sometimes kind of some spiky curves, but in a way, they look like they affect performance in this expected way. So we can just play with the first three, but just to make things simpler, here you have just plots using two of the three, which are the reward size as the x-axis and the reward distance as the y-axis. And we see different examples of participants in the competition, so agents. So the agent on the left, Joa Maru, is a very conformant system to these two dimensions. So we see that when the size of the reward is large and the distance is small, so this is bottom left in this plot, things are mostly green. But then we find a non-conformant system, Y young, and where it is even better on average than the previous one, but it's quite puzzling why the system is behaving like that. Maybe we don't have enough data and it's just a statistical artifact here, or maybe there's something really, really strange, especially happening with very large rewards. Maybe the rewards, maybe everything gets green or yellow in the or maybe very, very small rewards. Something strange is going on. So on the left, we can even just try to estimate capability boundary for both dimensions. But on the right, there's not much, it seems, that we can do with these two dimensions. So how would we predict performance? So this is not very difficult. This is not rocket science, but there are many ways in which we can do this. So one way is just For people, we take all the agents and all the instances, and we calculate global accuracy, which is 54.7% for the whole table of results. This is not very useful because agents, they don't perform equally. So what we can do is just the average of performance of the agent for all the tasks. And that's what people would do, the performance of the agent, the accurate performance of the agent. In this case, for this agent, which I don't remember the name was Juomaru. For Juomaru, it was 46.8%. And another thing that we can do is, if we think that these dimensions are predictable, we can just look at the cell. We can just use a kind of bin-in and say, okay, if we just look at that bin-in, in that bin, where we are, where the question mark is, it will be just 40%. And if we use a parametric model, just on the 2 dimensions and expecting that things go from green to red in a kind of a smooth way, we can use, for instance, a logistic or a multidimensional logistic function. We will get something like 73.2%, which is higher. So we have all of these different numbers. And what we did in this paper was adding another way, a non-parametric way of doing this, is what I'm going to explain in a moment, that we call them assessors, compared to all of these methods. And we apply this even to those systems that they didn't seem to have any pattern. So basically what we see is the middle result, which is just the accuracy per agent. That's basically what you do when you say this agent has 70% accuracy, and you try to extrapolate that for every new instance. That's what you get. You can get much better than that in terms of error and absolute error or squared error, depending on what kind of metric you want to use. And these are the 2 last columns on the right, and you get much better results, especially if you use all the variables, all the meta features, or you use just the 3 relevant features that we identified. Just by the 3 relevant features that we identified, we get almost the same accuracy or results than with all the meta features. So basically, what if these models are powerful enough, what we claim is that we have identified the 3 main dimensions that predict failure. And this is something that machine learning people and people in statistics say, well, what you have done is very easy, but it's not that common to do this exercise with our test data. And that's, but we can do a little bit more than that. And that's something that has been around for a while, but without a consistent name. And it was difficult to find some kind of a homogeneous account of this, and we called it assessor models. So let's see what this is, which is something that we have anticipated in the previous slides. So this is basically a conditional probability estimator of the result of a system pi on a situation mu. So again, we have this system and problem, and what we want is another model that we call an assessor that is going to predict when this system is going to succeed on the situation mu. So basically anticipating the success of the system. A failure model that you want to call them as well. That's perhaps sometimes it has been used in the literature. So you can train this on test data. And this looks a little bit challenging because usually test data is not for training, but you can use it for training the assessor. And the interesting thing is that you can use different situations, as you would do, but you can also use some other systems. So the failures of system A can be better anticipated if you have seen the failures of system B and system C and system D. So it's not only that you learn this model from a lot of instances, you also learn these models from a lot of other systems working on these instances. So basically you have these 2 spaces, the space of problems and the space of systems. And from these 2, you can characterize these 2 things at the same time and build a model that tries to give me a model, give me a situation, and I will tell you whether this is going to succeed. This is a little bit related to meta-learning, as you can imagine. You heard what meta-learning is. So this is yet another example. So we have a robot deliverer, and we have seen that it works worse in the city center, probably because it's more crowded, or but for many reasons. So the more you just deviate from the city center, the better results are. So you can describe the situation as a location. You would only have two meta features about the problem. Would be just the location, X and Y. So these would just help you map the errors of the system, or and in this case the R value, which is the success rate of the system. What we can do is we have different robotic systems and new that will be implemented. So we have learned from them, and these systems, it's interesting that we can parameterize them, that we can just extract features about these systems. Some systems maybe it's just the size of the robot or some other. Of course, in neural network, we have a number of parameters. There will be, of course, one meta feature that we could use for making prediction. And there's a lot of discussion at the moment with scaling laws in neural networks and all that. Of course, if you can characterize your system, so you have a population of systems that have been applied already on the same problem and instances, you can use all of this information to build a more robust assessor. So basically use information from a lot of instances and a lot of systems to predict how even a new system is going to behave. And there are a lot of applications, not only predicting instance performance, but even aggregating that and get population performance, anticipating what kind of design you have to do, for instance, in AutoML, combine the systems, of course, detecting anomalies. You can even apply explainable AI techniques on the assessor rather than the original system. You can do many things. Even maintenance and revision can be based on the assessor rather than the original model or the actual failure, but instead of that, the anticipated failure of the system. And of course, auditing and certification. So here you have an example. In the future, you're given this information about an AI system is 99% correct, don't trust it. What about your case? If for your case, for your disease, use an assessor, and maybe for your disease, this very good model, this very good AI system, the assessor predicts just 28% success because it's a very difficult case. And if that happens, then you don't want to use the system. So that's a more rational decision about when to use AI systems, in particular one AI system, but that might be another system for this particular problem that behaves better, and that's where you should use, and you can anticipate. And you can do many things with this and understand some of the questions that have been around in terms of evaluating AI systems. For instance, when you aggregate on all the systems, you have a difficulty function. When you aggregate on all the instances, you have an aggregated metric. But you can also get some insights on calibrations when you aggregate on the two elements of these assessors. So this gives you a lot of information, not only about the system, but some other systems, the problem, and you can learn a lot when you build these assessors. And now, with this kind of a trend of this is not enough, well, maybe another way of putting this is we can even do better. So predicting failure is not enough, because failure is not just the only thing, or it's not always easy to tell what failure is. So for instance, we sometimes assume that there's a ground truth, some labels in some classification problem or something, some reward functions that humans just add to your problem. And imagine this situation, which is something that we are going to have very, very soon, if we are not having that already. This is more like a multi-model models and kind of extension of language models, that they can just take a lot of different modalities and do tasks if you prompt them well. So imagine that this person is hungry. She takes a photo of the fridge and say, what can I make with this? And the robot just takes this question, what can I make with photo? and the robot just processes it, and the robot makes an order, basically decides that with some of these and buying some other things, you can have you can cook a potato omelette recipe, and then the system shows a video of how to cook these recipe, and then in the end, the user might be happy or less happy about this result. Maybe this person, she had dinner in the end, but maybe she says, but I didn't want to buy things. So the question is, the failure or success is much more complicated in these situations. It's not just even just a metric from 0 to 1, it's a kind of a loss function. It's much more complicated, and maybe there are many aspects that you want to anticipate. So instead of and another issue here is that this gets more complicated because it might change from user to user. So assessors should incorporate this kind of a description of the user as well. So an assessor would be something that would predict some kind of outcome given the problem, the system, and the user. And the user could be just one user or population of users. You can aggregate on different dimensions, get different results, and all of these aggregations, they are interesting for different purposes. If you want just to predict for one particular problem, for one particular system and one particular user, this is what you want to model. But maybe you can aggregate or you can model directly some of these other functions. So validity is complex. The other day I was playing with DALL-E, and I wanted 5 robots ordered by size, and I wanted to use as first image of my presentation. Yeah, well, you do with 3, you can succeed, but with 5, it gets really, really tricky. I played with different prompts, and sometimes I got 5, but they weren't ordered. So the closest I got is the 3rd image on the bottom, which is kind of ordered by size, but there's a kind of a mistake in the 3rd one, but at least you see 5 robots. Well, the last one is just not a little bit out of the image. I tried really hard, and maybe I'm pretty sure that's a right prompt that you think enough, you will get the answer. So validity or usability, this is more like a human and computer interaction problem. So when you want to predict whether a system is valid for you, then you have to consider the effort you have to put to give the right instructions. Here, I tried for 20 minutes and I didn't get, in the end, I thought, okay, I'm going to take the robots myself and I'm going to Photoshop it myself. And that's probably what you can do. User effort to extract the answers, to validate the answers. We really like these generators because it's very easy sometimes for us. We get 10 images and we quickly select one of them. So validating it is quite easy for humans. So the effort of extracting an image from 10 possible generated image is low effort. So that's good. But we need to measure that because sometimes it's not that low effort. Or the quality of the solution, of course, and the possible dangerous outcome. What if you get something that you know that it gets some breaks some of the filters of your system about the different things that could go wrong when you generate images, and of course the operational cost. 30 prompts using DALL-E. I don't know how bad this is for the planet. Well, I don't get the exact numbers, but yeah, these systems, even during deployment, they use a lot of compute. And if I can anticipate some of these things, maybe I can spare all of this effort, computational effort, which in the end, it is just energy cost. So we can do this from the point of view of capabilities. Each component can be captured by one or more capabilities. We can have a capability for the quality of the solution, but also for the efforts, or we can just build assessors for different components of validity. Just decompose the utility function. So what's the road ahead? And I'm going just to start closing. So there are many opportunities, and these opportunities appear because many of the problems at the moment in artificial intelligence, they don't come because systems are not good. It's because we are not able to anticipate when they are good and when they are bad. Explainable AI has given us a lot of progress, but they're changing a little bit the perspective into predictive AI systems. So I would prefer a worse system that is a little more predictive, that I can identify what makes it predictable. And that doesn't mean that you have to explain or to understand completely how it works, but at least I can predict it well. So this gives us some opportunities of things, especially machine learning people say, oh, I can use all of my power again just to build these assessors. Yeah, you can do, and even identify capabilities, latent meta features for predictability of these assessors. You can try things that are more comprehensible, which is the capability approach, or less comprehensible, which is a non-parametric approach, perhaps. If we can predict and we can calibrate our expectations about each particular instance, it's a more refined way of predicting when and where systems are going to go wrong. And of course, this comes with some challenges. And maybe some of you are just thinking at the moment, okay, we have this picture and now we have replaced it with this other picture. Now we can put more powerful into this smarter assessor that is trying to evaluate how the original model is behaving. And then you can think, okay, can I trust the assessor? Well, this is a question here as well. But the interesting thing is these two systems, these two robots that we see on the screen, they can be very different. For instance, the system in the middle, they can be developed by one company, one organization, and the assessor by another organization. The green robot can be a reinforcement learning agent, and the assessor in yellow can be just it's just a prediction model. It's not even an agent. So it's easier to understand and to control a supervised model than to control, for instance, a reinforcement learning model. So yeah, of course, there are some challenges here about the trust in the assessors, but we have to take into account that this changes a little bit the kind of system we are talking about in the green system versus the yellow system. So final slide. All of these should be plugged into the proposals for assurance. You want to call them for Trustworthy AI. So there has been some proposals of model cards. Whenever you release a model, you have to follow some kind of, you have to tick on several things before it is released. This is necessary. This is here to stay. There's also this idea of ethical black boxes, and the term black box in AI is usually associated with neural networks or some other machine learning models that are not comprehensible. But the idea of black box here is the same idea as black boxes in airplanes. So you have a problem with a robot, your self-driving car crashes, and you need to have some kind of a black box that has all the information, all the parameters, and a recording of what the system was doing. This should be imposed not only in self-driving cars and airplanes, but probably in all AI systems, complex AI systems that are deployed. And the third thing, and this is my plug here, I think that we should have for each deployed AI system in the future, we need to have this assessor model. So the vision is that whenever or for every deployed AI system, we have to accompany the system with a capability profile, or if possible, an assessor model that is going to anticipate how the system is going to work for each possible instance, as accurate as possible. And if these assessors are not good enough, you cannot predict this well, then you shouldn't deploy the system. And that's it. Thank you very much.
Thank you, Jose. It was a really wonderful talk. So I have lots of questions. So maybe I will start with a first question. So at the beginning, you were saying that performance may change with data distribution, or like that if you train your model on ImageNet and you don't really know what the performance can be on other data. So I was wondering whether like like data normalization could be one solution, or at least part of the solution to it. This is something I think which people are not talking enough about it and not doing research enough about it. But in other areas, like in fMRI analysis, for example, people are really developed very, very smart normalization algorithms to make data comparable, right? So they're registering the MRI image to fit it in a common model and make things comparable. So do we need more data normalization research to at least partly make things more comparable?
Yeah, well, I think this can be useful in terms of expectations, and in terms, I think the example of MRI, this is a good example, because in the end, what you are interested in is how well this system is going to behave for a population, and you have this actual population. You are not interested in any kind of fictional population. So you can say, okay, this system works well for this hospital, and I want to move it to another hospital, and things are a little bit different, and I want it to work as well and for the other hospital. And then maybe the distributions change, and maybe there's something that by normalizing you can do some fixes. Then maybe you realize that you have older people in population B and population A. And because of that, maybe you have different success rates. And that's something that you can't really fix. It's something that's going to happen unless you have been having some kind of ageism or bias against older people. And then if that's the case, you can fix it, because maybe in hospital 1, you didn't have enough of that population. But normalization, especially with images and some other way you can do this, I think that's very useful. But in some other cases, maybe it's not going to be enough. And it's also useful to understand, even if the distribution doesn't change, why you fail, where you fail, and in terms of instances, what's particular in this instance that makes the system fail. And explainable AI has done a lot of progress in this, especially in image classification and some other image processing in general. But in some other areas, for instance, in reinforcement learning, there's so much to learn about why a system fails. It's much more complicated with all of these state action spaces.
Yeah. Do you think we need more interactive approaches to XAI? So because if humans explain, if one human explains something another human, it's often like a dialogue, like an interaction. You ask a question, I try to answer it, and then you ask a more detailed question. So it's not like one-shot explanation. Do we need more of these type of approaches?
Yeah, probably. But I think that perhaps the critical question is, even for humans, can you anticipate what is going to happen? And maybe one way of, after maybe this dialogue or this kind of explanation process, you would give an image or another problem to a human, and do you think that the system is going to be correct on this or not? And maybe you don't need to go through the same processes, but maybe you see that the image has a lot of clutter, and because it has a lot of things, you don't know what label the system is going to tell, but you can say, okay, as a human, I see that this image is going to be complicated for this system. And I don't understand why the system said A rather than B, but I know that there's something in this image that makes things complicated for the system. And this is the kind of questions that I would like to ask a person to certify that the person has really understood the consequences of using the system. Not only that question, but I would include in this kind of interaction. So explainable AI has to go into more human studies, more like, for instance, software testing. They do, and sometimes in computer science, we are reluctant just to go into that. But for instance, we can ask for help to the human-computer interaction teams in our departments, and they are more, and of course, psychologists about. Without these perspectives in explainable AI, we will fall short into understanding whether just the human is happy with the explanation or is actually really using what the human has understood, just to say, okay, now I will use the system, now I won't use the system. It is a critical question.
But like, does it mean that what you kind of really need is some kind of method which provides also the uncertainty. So if you would have a method which not only gives you the prediction, but also a good estimate of the uncertainty, would that be enough?
Yeah. If you have a very good uncertainty estimation, for instance, that happens to be very good with language models, you can use that. But what happens is that in many cases, you can get much more if you build a model using the failures not from one system, but from many systems. You can get more data than just from one system, and one system can only give you the uncertainty estimates from its own experience, which is basically just one system. So even for anticipating new instances, maybe if you have seen another system failing on this instance, maybe you haven't tried with this system, but you can really say, oh, every other system has failed with this instance. So, well, for the moment, even if this new system you have built is fantastic, much better than the rest, I can anticipate that maybe this case is going to be hard as well for the new system. So you can do much more than just looking at, and sometimes even if you can do more or less the same as with language model, is kind of challenging to build a good assessor about a language model. You need at least or around the same level of parameters to get a good evaluation of the original language model. It's better than the self-assessment. But the interesting thing is sometimes you can, these things can be done by different teams. And that gives you some kind of reassurance. Okay, give me your system, give me even your test data, I can just go and test it, and I will evaluate the system. And this is kind of what the purpose of the assessor, and try to predict where the system is going to fail. That gives you a little bit of independence, especially for regulators, about trying to do this, which is independent from self-assessment. But of course, the first thing that we should do as AI people is let's try to build systems that have good confidence estimates. If a system doesn't give you good confidence systems, then yeah, the applicability is limited.
We have some questions from the audience. So your focus was mostly on the technical functional types of risks in AI. So what about social risks, like cyber attacks or fake news, adversarial attacks?
Well, there's well-intentioned use of AI, and many things can go wrong. The typical thing is local maximization. This goes really, really bad at a global level, and there's something that even you have goodwill with AI, you can mess a lot of things up. And another thing, malicious use of AI. And that's even more worrying because AI is becoming very powerful, and some people start, and I don't think that perhaps fake images is the worst problem that we have at the moment, but there are many other problems, especially in cyber attacks, that AI can use some kind of more sophisticated attacks than just algorithmic attacks that were just designed. It's just a question of scale and a question of capability. And with AI, you have both things. So in some applications, such as cybersecurity, yeah, it's a big concern. But I think that some of the things that I was discussing you want to use a malicious use. I think that it's more like in cybersecurity, we have to be prepared, but it's not that much about understanding what these systems do. I think it's more like that the goodwill applications of AI, that sometimes they go wrong because you choose the wrong utility function, or because sometimes you use a very utilitarian perspective, and sometimes society cannot be integrated into a single formula. You have to be very interactive about this. Yeah.
So how do you define success and failure? So how do you know that what you expect to be a success status is actually a success status?
Yeah, that goes well with the last part of my talk, where it's predicting failure is not enough, basically because many times you cannot define failure very well. It's not even that you can just put reward function, then that sometimes it's positive and sometimes it's negative. This has been discussed in alignment problems. It's not you're going to have a system and there's going to be a human just giving you points all the time about where you're doing well or you're doing bad. It's much more complicated. And that's why we need to perhaps, instead of just trying to integrate everything into one utility function of success and failure, try to dissect these into several components, and maybe you realize that you are good on 4 components, but bad on 5 components. It's a little bit like the SDGs. You're not good for the planet, you're good for humanity. There are many ways in which, and sometimes you have to find trade-offs and disagreements. And I think the important thing is this idea of values for people. Well, people have different values. So unless you put the user and the particular user, not the whole of humanity, this diversity of human people having different values, unless you put that in some way in your formulas, if you don't consider them, you're not going to capture failure and success well.
Mm-hmm. So would you say we need to develop our own capabilities in developing better prompting? Or like getting better results out of the AI system relies on better quality of prompts, like asking the right question gives you a better result. So do you think we also need to educate the user?
Yeah, I think that has been the case in human-computer interaction. So the first time, we see keyboards, screens, the mouse that we are using, all of them, we have been trained to use them. And maybe kids, they think it's natural for them, but for some of us, when there's a new thing introduced, we need some time to adapt to that system and to learn how to use that system. The thing about, for instance, prompting in language models is it becomes really sophisticated. The only thing that I think that is similar is programming in a way. But programming comes with some kind of has been very well studied, and we've gone through that for decades about how to teach programming. And programming is, you know what you're doing. With prompting, is in a couple of years, people say, oh, you do chain of thought, you can get much better results from your system. It has been evolving a lot. So I think that, we'll need to learn how to use these systems. And of course, some versions of the system will try to make this easier. But we'll need to adapt to these systems. In the same way, we adapt with our digital assistants, and we know that some questions we are not going to get an answer. And after using them for a couple of months, we know what things we can ask and how we have to ask them.
Yeah, I think also like humans anticipate the expectation of other humans when explaining, when providing an answer. So do you also think we need to have more of this in AI, like to try to build AI which kind of has some user model?
Yeah, I think that that's one of the problems of AI. AI works in very different ways, and humans, they're used to interact with humans. So we expect a little bit, even at the detailed level, you don't know what a human is going to do. We know what's more or less expectable. And with AI systems, we break some of these. So either we train ourselves to these new behaviors, and that's going to become more and more challenging because there are going to be many different behaviors depending on the techniques, the applications, and a single human is not going to be able to cope with all of this technology coming. And another thing is perhaps that even if they are not the most powerful techniques, approaches, we have to try to do AI systems that are more human-like. Because if they are human-like, even if they're they have a little bit less performance, maybe if they're human-like, it's going to be easier for the mortal human, the mortal user to understand how they behave. And maybe we have to go in that direction, at least for some applications. We need more human-like AI systems.
Mm-hmm. So we have a last questions from the audience. Is there an environment similarity calculation used in your validity modeling?
Environment similarity.
Or context similarity?
Yeah, well, I'm not sure if I understand the question correctly, but this perhaps in terms of the problem space, you have different.
I think so, yeah.
Yeah, different instances. Yeah, that's a good question because, for instance, something that you can do is for this assessor, you could use something like an nearest neighbor predictor. for instance. That basically what we do with just to use the similarities of the elements or the inputs to make the prediction. And if half of these inputs are basically the description of the problem, which in this case will be the environment. So you have kind of similarity metric between the environments and a similarity metric between the systems. Given a system and given an environment, you could predict very well. So you could use at least this approach. If you have these similarities, you could encode them in some kind of a distance matrix and use kind of a distance-based approach for prediction there, rather than using some other techniques such as neural networks for your assessor or something like that. Yeah.
Like multitask learning or something. Yeah.
Yeah.
Good. So thank you very much, Jose, for the interesting presentation and the discussion. It was a pleasure. And yeah, with that, I think we are done, and I hope to meet you soon.
The pleasure was mine. Thank you for the invitation.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
you.